Hello, my name is Seth Russell. This work was co-developed with Peter DeWitt. We are both with the Department of Biomedical Informatics at the University of Colorado Anschutz Medical Campus. I'll be talking today about predicting intracranial pressure monitoring placement in children with traumatic brain injury. Before I begin, I have a few disclosures. This work was grant funded by a couple of sources with Tel Bennett as the principal investigator. This work has been accepted for publication in the Journal of the American Medical Informatics Association, publication date pending. And although Peter's name and my name are on the slides, this work would not be possible without the effort and guidance of many other people. The motivation for this study is traumatic brain injury, which is a violent blow or jolt to the head or body that can cause temporary or permanent complications up to death. Swelling is a common serious complication. Annually in the United States, traumatic brain injury causes 2,200 pediatric deaths, 35,000 pediatric hospitalizations. To monitor and track brain swelling, an invasive procedure is performed to install a device called an intracranial pressure monitor into the skull. Clinicians currently make decisions about ICP placement with traumatic brain injury without the benefit of an accurate clinical decision support tool. The aim of this study was to develop and validate models that predict placement of an ICP monitor. Models should update individual predictions as new information becomes available during an intensive care unit stay. Our study was a prospective observational cohort study from September 2014 through January 2024. 389 children with acute traumatic brain injury were admitted to the ICU. 138 or 35% of the 389 participants received ICP monitoring. This study was approved and granted a waiver of consent by the Colorado Multiple Institutional Review Board. There are many things that I feel are novel about this work. I think that the real secret sauce of this project is the data. Although others can also collect data like this, it isn't just available for anyone outside a clinical setting. This also is the part that data scientists and ML engineers usually can't get on their own. This project started with manual extraction of data from the electronic health record, also known as EHR, performed by the study team, which includes MDs and residents. This information was entered into REDCap, which is a self-hosted, open-source, web-based system that we could then extract from for our model training. As REDCap was configured to allow for multiple entries in some areas, the dataset had about 276 columns covering the major groups of areas shown in the image on the left. As time progressed, we were able to get data directly from the EHR. This involved SQL statements to identify and extract desired information. The selected information is saved as CSV files, then securely delivered to our team. EHR data includes items such as nurse-validated vitals, observations, and diagnosis codes. We also were able to get laboratory results from the EHR. This reduced many sources of error, as humans are not very good at copying data from one source to another. This EHR dataset was in a long format, as shown in this mock-up table on the right. Now that we had access to these two data sources, we needed to combine them into one. I'll review a few points about how that process worked. Categorical variables were dummy encoded, converted to Boolean indicator columns. Invalid vital signs were set to null. Time periods without a value used last observation carry forward up to the point of ICP insertion or the maximum time of 24 hours after admission. Variables with no previous value were set to a healthy default value. All variables were then categorized as static, for example, age, sex, injury mechanism, or dynamic, for example, blood pressure, sodium level, and centering and scaling by variable type was performed. This resulted in about 35 variables and 270,000 rows of data from our study. In addition to the aim I already mentioned, a sub-question we had was how accurate can models be with less information? Key areas identified by clinical experts were computed tomography scans, which is basically lots of x-rays taken in an area, around an area of the body to get an internal 3D view, and invasive blood pressure observations. Or what impact would the following have on a model if a CT scan can't be done, for example, at a facility without expensive medical equipment, or the patient can't be safely transported to a CT scanner? Or invasive blood pressure is usually an indicator of severity based on an assessment of medical team and requires a sterile medical procedure. Concretely, from our source data, we had the 4 following subsets of data used for training. The statistical and machine learning models we built were trained with each of these different combinations of data. Lastly, we split our data temporally into training and testing sets based on encounter start date. We decided to explore several options for creating predictions of whether or not someone would receive an ICP monitor. There are many machine learning and statistical methods available, but we wanted to try a few common ones, such as logistic regressions, support vector machines, often referred to as SVMs, generalized estimating equations, generalized additive models, and one deep learning method, a neural network utilizing long short-term memory layers. Of this list, I'll talk in more detail about the logistic regression and neural network models. We used R for this project, and I thought it would be helpful to show you a few code snippets to help you see how it works. These slides are available later, so if you want more time to review our code, you can. I'll show snippets of code from our pipeline for standard logistic regression and deep learning. This slide shows the relationship between the model input variables and the desired outcome of ever receiving an ICP monitor. Here we configure multiple formulas to create models with the various subsets of the available data. For example, on line 34, we have no CT and no invasive blood pressure. On line 37, we have no CT and invasive blood pressure. On line 39, we have CT with no invasive blood pressure. Then we fit a GLM, also known as standard or unpenalized logistic regression. So we also used R for the deep learning portion of the modeling effort. If you're familiar with Python, Keras, and TensorFlow libraries, you may recognize some of these function calls. While using R for deep learning is possible, after having used R for deep learning for this work, I recommend using Python or a more natively supported language. The main reason for this is that we have R calling Python, which then calls C and/or CUDA code via various intermediary wrapper libraries. In my experience, this can be quite difficult to debug, and search results for similar setups are hard to find. In this block of code, we build the number of desired LSTM layers, which is provided as input to the function. For those that prefer a model network architecture diagram, this is a high-level view of how the model layers were configured that gave the best results. Input data on the top left is followed by a masking layer, followed by a dropout to reduce overfitting. Next, we have a dense layer, then 2 LSTMs, 2 LSTMs, 4 LSTMs, and then 64 LSTMs, followed by another dropout layer. And lastly, the output of a binary prediction. Next, we configured the optimizer and which statistics will be calculated during model training. We used callbacks to improve model training, including early stopping, where the training is not improving results, reducing the learning rate when no progress was made, and checkpointing the best model from a training run for easier recovery and reuse. One area that I find often left out of discussions and papers, conference talks, etc., is how someone found the best hyperparameters for their model. While some datasets have known model architectures that are proven to work well, such as ResNet for images, what about domains like ours that don't have established best practices? We decided to do a random search over the hyperparameter space and use the best performing models to inform a localized search to find the best architecture. This random search included a range of learning rates, validation splits, a range of dropouts, multiple optimizers, number of layers, layer sizes, and random seeds. Total combinations is about 30 million, which is much too large for an exhaustive search. The key here is that we create a grid of all possible combination of options, then randomize the list for a queue of model building. In our model building pipeline, we had 3 queues. We used GNU Parallel to run and manage jobs. Once we started our script, we mostly watched the lights blink for a few weeks and occasionally gather and review model training progress using the created log files and TensorBoard visualizations, such as the one shown on the bottom right. In this graph, the black line is the loss on the training data, and the blue line is the loss for the testing data. Note, testing loss initially improves, but at around 50 epochs, testing loss goes up, which is bad. That's overtraining. Also shown is a summary of the hardware used for model training. The end result of this process is that we found a network architecture and model hyperparameters that worked well for our input data and desired outcome. Here's a few graphs of showing how our models did. For comparison across models, we calculated F1 at each time point up to ICP placement, or 24 hours. To make the graphs easier to view, I've shown just the first 12 hours after admission. The best performing model, shown here in yellow, is the LSTM model that I showed some code for earlier. The next best model is the pink line from the unpenalized logistic regression, also shown earlier. Of particular note with our data, the brownish line for SVM performed the worst. Also, to get a better idea of how many accurate predictions are being made, we created a cumulative F1 graph shown on the bottom row. That sums up every F1 from every time point so you can get a better idea of how the ups and downs average out over 12 hours. Linear models are great in that they have interpretable weights that can be used to explain how a prediction is generated. The large green, red, yellow table shows model coefficients for 3 of our models. Large positive coefficients, shown in green, result in increased likelihood of ICP placement. For example, CT scan showing internal bleeding. Negative coefficients, shown in yellow, with a large absolute value result in reduced likelihood of ICP placement. For example, a high GCS score, which shows excellent mental status. The generalized additive models, GAM, allow for visualization and interpretation of the marginal impact of a variable over time. By marginal impact, I mean after integrating out the impact of other variables. The 4 visualizations on the top right, sorry, one is covered a little bit by my talking head. The x-axis shows the value of the predictor. In this case, non-invasive systolic blood pressure, centered and scaled for model input, and the y-axis is the estimated probability of an ICP monitor being placed. It appears that patients with extremely low systolic blood pressure, less than 2.5 standard deviations, are at a high risk of getting an ICP. The 4 visualizations in the bottom right, with colors and contours indicating the estimated probability of ICP monitor placement. White regions indicate no data were observed. What is notable about this figure compared to the one above is that we can see the majority of systolic blood pressure observations are within 2 standard deviations of the mean. Within the first 10 hours of the encounter, higher systolic blood pressure is associated with higher probability of ICP insertion than low SBP. The relationship reverses later in the stay. Extreme SBP late in the encounter are associated with low probability of ICP insertion. These explanations make the MDs happy and also give insight into treatment options. With LSTM, you get more accurate predictions but no proof or validations to show clinical experts to help them trust the result or give insight on what factors contribute to poor outcomes or improving outcomes. What about SHAP, some of you may say? Turns out SHAP has very weak and intermittent support for LSTM layers with the deep explainer methods. Although it is billed as supporting deep learning with deep explainer, TensorFlow, and Keras models, it apparently only works with some layer types, and those layer types only work in some versions of SHAP. Unfortunately, the current version of SHAP doesn't support LSTMs with the current version of Keras and TensorFlow. After a couple of days of version compatibility research, I was able to find a version from about 2 years ago that supported LSTMs. However, we did not want to repeat our entire work on old versions of TensorFlow, Keras, and SHAP. So as the developer of these models, this makes me sad. In conclusion, we tried a smorgasbord approach to modeling to see if we can predict the need for an intracranial pressure monitor placement. With these collection of models, we've set a baseline for this prediction and hope to continue this work in the future and improve the care of pediatric traumatic brain injury. My slides are available at this GitHub repo. Please reach out to me with any questions. Thank you.